Today we are going to discuss an important topic, that of information retrieval model, and in particular we will talk about two models, namely Boolean and vector. All this we remember is in the context of the relationship between natural language processing and information retrieval. We have remarked already that both the fields process text, and how in response to a user's query a document is retrieved that is relevant and satisfies the information need of the user is the main concern. Now, in this particular lecture we will essentially dwell on this particular point as to how the terms of a document are weighted, how the terms in the query are weighted, and then the relevance of the document is computed. So, proceeding, we just remember that the retrieval process happens in the following way. There is a user interface and the user information need is expressed in the form of a query. The query is used for searching the documents are ranked and shown back to the user. As a background offline processing, the text database is created and a database manager module produces the pages of the information, and these are the pages which are shown to the user. They are indexed and various kinds of text operations are carried out to match the user's query along with the indexed pages. So, this is the basic schematic. There is this offline processing on the pages and online processing on the query. Now, query to document transfer, so to say, happens through a list of documents which are indexed. So, there is this index table. The queries consist of these n words. A particular query is shown here, q1, q2, qn. So, this could be a query like tourism to Taj Mahal, which has 3 words, q1, q2 and q3, tourism, to and Taj Mahal. The index table would contain the terms like tourism and then Taj Mahal. 2 will not be contained for reason which was explained last time. 2 is a stop word. It is highly non-discriminatory word. That means, it does not have any specific role to play with respect to the specific information of the document. So, index table contains these k indices I1 to ik, and when we have the documents displayed such that highly relevant documents are occupying high rank in this list, then the user's information need is satisfied. So, we have a ranked list of documents here. Now, what happens is that the user gives his query to the search box, then database, algorithm, data structure, all these areas of computer science come into play. The index table and the documents are created. There is a relevance feedback given to the user in terms of the documents which have been retrieved, and this closes the loop. Then progressively the quality of the documents retrieved improves. We recapitulate the method to find out the accuracy and the quality of the retrieval. There are 3 parameters, namely precision, recall and F score, which are used to calculate the accuracy of the retrieved documents. So, you can see here precision is defined in terms of A intersection O divided by the size of O, where this diagram is there to explain A and O. O is the obtained list of documents, A is the actual list of documents, and we should look upon them as sets rather than lists. So, A intersection O is the documents which are retrieved from the actual set. Okay. There is this agreement area A intersection O, where actual documents and obtained documents agree. Now, this precision is a ratio of A intersection O and O. This means what is the proportion of obtained documents that is correct. This is precision. Recall is the ratio of A intersection O and the size of A. So, this is the proportion of actual documents which are retrieved, actually correct documents which are retrieved. F score is obtained from the harmonic mean of P and R, 2 into P into R divided by P plus R, and we remarked last time that if one improves on harmonic mean, automatically geometric mean and arithmetic mean also improve, because harmonic mean is the least of these three means. Now, precision, recall and F score are easy to calculate mathematically, but in actual practice for information retrieval, when documents are retrieved and the document list is shown to the user, a ranked list of documents is shown to the user, then precision is easy to calculate, but recall is not. So, let us understand this particular point. Precision is easy to calculate because we have the list of documents in front of us, and let us say we decide to go up to the kth position. K could be 10, 20, 5 and so on. Normally, what is done is shown here. I would like to draw a picture. So, we have the ranked list of docs, and here are the documents D1, D2, D3, D4 and D5. Now, the concept of P at 5, that is precision at 5, is P at 5 is that out of these documents, let us say D2 and D4 are relevant, D2, D4 are relevant. Then P at 5 is 2 by 5, which is 40%. So, precision is quite easy to calculate, but consider what will happen when we want to calculate recall. So, how will that be done? We have already seen that out of these 5 documents, D2 and D4 are relevant. Okay. So, they are from the list of actually relevant documents, but if we want to calculate the recall, then we will have to know the actual list of documents which are relevant, If that number is known, then in that case we can divide these values, these D2 and D4 by, that is 2, by the total number of actual documents. So, at the web scale, when we have the whole internet to be considered, then it is impossible to know the actual list of relevant documents as they exist on the web. So, computing recall therefore, is a very difficult proposition. It is impossible to do so at the scale of the web. So, that is why looking at the slide again, we are commenting that precision is easy to calculate, recall is not. Given a known set of pair of Q and D, that is query and document pair, relevance judgment is produced which has value 0 or 1. So, Q comma D is 0 if the document D is relevant for the query Q, and if it is irrelevant for the query Q, otherwise it is 1. So, 1 indicates this document D is relevant for the query Q, and this is typically done by human evaluation. So, human beings actually sit down with a query and produce and launch searches, and whichever document are retrieved, they actually read them, and from their reading, if they see that this document is relevant to the query, then they produce a mark 1 along with the query and the document, and this is the way a relevant pool of judgments is created. Okay. So, now we look at this graph here on the slide, which is the relationship between P and R. This is the typical behavior of precision versus recall curve. typical behavior for recall versus precision curve. So, as recall increases, precision falls and vice versa. So, precision and recall have an inverse relationship. Now, let us see why this behavior is seen. We would like to show it on the paper. So, we have already seen that precision and recall are computed from the actual and obtained entities. So, this set is A, this set is O, A is actual and O is obtained. Now, P is equal to A intersection O divided by O. Recall on the other hand is A intersection O divided by A. Now, and we are saying that the precision versus recall curve P and R curve comes this way, it has a falling curve. So, this is a typical behavior and it is important to reflect on why this is the case. Now, let us see if the recall must improve, then either A should go down or A intersection O should go up, that is increase. Okay. So, now let us assume that the actual set of entities which are correct, that does not change, let us suppose. Okay, let us suppose the A does not change. So, if A does not change, the only way recall could go up is by increasing O. Okay, by increasing O. So, as O increases, the denominator of P increases. Numerator also increases, but as we know that the same entity appearing in the numerator and the denominator would make the denominator more predominant than the numerator. What we mean by this is that as O increases, denominator increasing, numerator increasing, the effect will be felt more from the denominator. Okay. So, that means the rate at which P will increase due to numerator will be less than the rate at which the denominator, the rate at which P decreases because of the denominator. So, let us write these points down, why P versus R curve is decreasing. So, assume A is constant, which is the actual set of things. A is constant. To increase R, therefore, O should increase. To increase R, therefore, O should increase. So, P A intersection O by O, both numerator and denominator increase. So, P goes up due to A intersection O going up, P goes down due to A going up, O going up. Since O is denom, P effectively decreases. Okay. So, that is the reason. Now, another way P could increase is by increasing the overlap between A and O. So, both A and O remain same, but it is just the fact that O goes inside more into A and thereby A intersection O increases. So, if that happens, then of course, both precision and recall increase, but normally that does not really happen. Okay. So, going to the slide now, we have understood the behavior of precision and increasing one decreases the other. So, here we are making an important remark, unless additional knowledge is given. So, P and R have inverse relationship with each other. As recall increases, P would go down. So, is that sacrosanct? Will that always happen? That will not happen if it so happens that the overlap between A and O decrease without disturbing the actual values of A and O. So, that means the intersection area A and intersection area between A and O increases. So, this can be done by increasing the effectiveness of search by injecting additional knowledge. Okay. So, which is where the role of natural language processing comes in case of information retrieval. So, how does one bring the O area closer into the A area, so that the intersection area increases? That would increase only if we have more effective search, and that it is seen typically happens if we inject more knowledge into the system, if we make use of the text which is retrieved, the information content of the text which is retrieved, the meaning of the document and so on. So, that is where language processing plays a role. So, proverbial P versus R curve, which is decreasing, can be offset. Okay. This problem can possibly be solved by introducing language knowledge, domain specific knowledge, meaning information and so on. Okay. So, let us mark this point here on the slide, that P is inversely related to R unless additional knowledge is given. Now, there is this important parameter which we started discussing, precision at rank k. Choose the top k documents, see how many of them are relevant out of them. So, P k is equal to number of relevant documents divided by k. This is P at k, precision at rank k, and the mean average precision is obtained, in this way, that is 1 by L into sigma P k. So, what it means is that, why is it called mean average precision or MAP? There are two means, as you can see here, two averages. Mean is an average, average is also an average or a mean. So, what happens is that for a particular retrieval, we can vary k. So, we can keep on calculating different precision at 1, at 2, at 3, at 4 and so on up to let us say about 100. So, we collect all these precision values. Then the number of times these precision values have been calculated, this sum of precisions are taken and we divide it by the number of times this has been done. Okay. And we do it for many different queries. So, the precision values, the average precision values of different queries are taken, and when we take the average of these average precision values, we get the mean average precision. So, MAP value is a very important parameter for calculating the effectiveness of the search system. Now, we do a small sample exercise. Suppose our document D1, the first document is Delhi is the capital of India, it is a large city. Okay. D2 is another document which contains the text Mumbai, however, is the commercial capital with $1 million inflow and outflow. So, two pieces of text, two documents, let us say Delhi is the capital of India, it is a large city. Mumbai, however, is the commercial capital with $1 million inflow and outflow. So, the words in red constitute the useful words from each sentence. The other words, those in black, are very common and thus do not add to the information content of the sentence. So, things like they appear in all documents, all sentences. So, the presence of does not make D1 anything special, and similarly does not make D2 anything special. So, the vocabulary is constituted of the red words which appear in these documents. That means, they are the words which are not stop words, they are the content words and are important for the documents. So, here the red words are unique red words are 11 in number. Each document will be represented by a 11 tuple vector, each component being 1 or 0. So, if Delhi is the first word in the vocabulary, then the vector of D 1 will have a 1 in position 1. Okay. Then, if capital is second word in the vocabulary, then Delhi will have this document D 1 will have a 1 in the position of capital. Okay. Similarly, for India, large and city. Mumbai will come after that, we will have a 1 there. Commercial and capital will come after that with $1 million inflow and outflow. So, for each of these words, we have a position fixed in the vector and we will make that position on or off depending upon the appearance of the word in that vector or not. So, this is the way the vectors are created, and what we do having obtained those vectors is the point under discussion now, and we have to discuss what is called the IR model. An IR model is formally defined as a quadruple. It has 4 components. D is the set of documents, Q is the set of queries, F is a framework for modeling the document, query and their relationship. So, F is a framework which represents the documents and the queries, and R Q I D J is a ranking function. It returns a real number expressing the relevance of D J with Q I. Okay. So, R Q I D J captures the relevance of Q with the document, the query and the document. Okay. So, these 4 tuples, let us remember the set of documents, the set of queries, the framework for modeling the document in the query and the relationship, and R is the ranking function. The index terms are created from the documents. These are the keywords which represent a document. Semantics of the word helps remember the main theme of the document, and generally the index terms are nouns. The prepositions, conjunctions, articles, etc., being present in all documents get dropped, which is why they become stop words, and we assign numerical weights to the index terms to indicate their importance. So, here is a schematic of what is being said here. We have the documents, the index terms represent the documents, the query, which is an expression of the information need of the user, is matched with these documents, and a ranking is produced depending on the relevance degree. So, there are a number of information retrieval models, and we discussed 2 of them here. The third, which is the probabilistic information retrieval model, will be discussed after this. So, the importance of the index terms is represented by weights associated with them. Let us suppose T is the number of index terms in the system. In the example for Delhi and Bombay discussed a while back, T value was 11. There were 11 terms which were the keywords in the system. So, let T be the number of index terms in the system. K equal to K 1, K 2, K 3 up to K T is the set of all index terms. K I is a particular index term, the ith index term. D j is a document, W I j is a weight associated with K I D j. Okay. So, that means, what is the weightage of K I, an index term, with respect to this document D j. W I j is equal to 0, and this indicates that the term does not belong to the document. Vec D j is a vector of weights, and they are fixed this way. W 1 j is the weight of the first keyword with respect to the j document. W2j is the weight of the second keyword with respect to the jth document. W_tj is the weight of the tth keyword with respect to this document dj. It is a weighted vector associated with the document dj. Gi v vec dj. So, when the vec dj is given, then Gi is a function which can extract the weight associated with the pair k I dj. Okay. So, it returns the weight that is indicative of the importance of the keyword k I for the document dj. Proceeding further, we first take up the Boolean model, which is the simplest model and is, let us say, the basis for subsequent models. It is a simple model based on set theory. Only and, or, and not Boolean operations are used. The queries are specified as Boolean expressions. They have a precise semantics in terms of absence or presence in the document, and the formalism is neat. So, suppose we have this query k A and k B or not k C. So, the semantics of this is that give me a document which contains the word contains the keyword k A and either k B is present, another keyword k B is present, or the document does not contain the keyword k C. So, it is a document which contains k and also satisfies the requirement that either k B is present or k C is not present. Okay. So, one could think of a query based on this particular expression. So, give me any document which contains the word Delhi and contains the word Qutub Minar and either contains the word Qutub Minar or does not contain the word, let us say, parliament. Okay. So, what kind of query would that be? Can a user be expected to form his query this way? So, that is the main criticism against the Boolean model. The semantics is clear, but is not natural enough for a user to form this kind of queries. So, terms are either present or absent. Thus, Wij belongs to the set 0, 1. So, Wij value can be 0 or 1. Now, from the query k A or k A and k B or not k C, we can form a document vector in disjunctive normal form. We call it vector of q, d and f. Now, k A, k B, k C, they occupy 3 positions of a tuple. So, the first position is for k, the first keyword, second position for k B, the second keyword, third position for k C, the third keyword. So, one could expand this query and put it in a disjunctive form. So, this would be k A and k B or k A and not k C. So, we write it down to see how these vectors are produced. So, q is k A and k B or not k C. So, we have a tuple with 3 positions. So, this is the position of k A, this is the position of k B, this is the position of k C. Now, q can be written as k A and k B or k A and not k C. So, this gives rise to a tuple 1 1 1 or 1 1 0. Since k C is not absent here, we can say this is the do not care element, and that can be either 1 or 0. So, this is equivalent to k A and k B and k C, or k A and k B
and not Kc. So, Ka and Kb and Kc, Ka and Kb and not Kc, and similarly this will be either Ka, Kb not Kc, which is expressed by this, or it is Ka not Kb not Kc. Okay. So, these three vectors are obtained from the query Ka and Kb or not Kc. So, now we look at the slide again, and we have the QDNF vector form in this way 1 1 1 or 1 1 0 or 1 0 0, and a conjunctive component of vec QDNF is one of the elements which is linked by OR with other elements. So, 1 1 0 is a conjunctive component. Proceeding further, now how is the relevance found out of a document? So, Q is K and Kb or not Kc. So, here we have these three spheres with respect to Ka, Kb and Kc. Now, this particular area belongs to both Ka, belongs to all of Ka, Kb and Kc. So, 1 1 1 is the representation of this intersection area. 1 1 0 this particular area, and that is the intersection of K and Kb and Kc being absent. This area belongs to only Ka and this is 1 0 0. So, similarity of a query with a document Dj is asserted to be 1 if there exists conjunctive component from the vector of Q such that the conjunctive component belongs to the DNF representation of the query vector, and for every component of the conjunctive vector we have a match with the document vector representation. So, that this particular term essentially means that the components of the conjunctive component of the query vector should each match the components of the document vector. That means, whatever is present in the query should be present in the document, whatever is absent in the query should also be absent in the document. So, this is the essential meaning of the similarity between the query and the document. So, this is quite easy to compute. However, there are a number of drawbacks of the Boolean model. So, we have said already that retrieval is based on binary decision criterion with no notion of partial matching. The Boolean IR model, the Boolean model of matching and relevance insists on complete matching. Each term must be either present or absent. No ranking of the documents is provided. So, there is no graded scale with respect to the ranking. That means, the documents are either similar or dissimilar to the query, because whatever is present in the query must be present in the document, whatever is absent must be absent in the document. So, this is another drawback. Information need has to be translated into a Boolean expression, which it is very difficult to do for most users. So, how can you say give me a document which has Delhi and either contains the word Qutub Minar or does not have the word parliament. So, these kind of queries are never asked by the user. The user will simply put a query Qutub Minar in Delhi. Okay. Users do not even specify negation. So, this kind of query representation in terms of Boolean is unnatural. The Boolean queries formulated by the users are most often too simplistic. So, since this is in terms of presence or absence, the queries and the thinking process also thereby becomes constrained and is simplistic. And as a consequence, the Boolean model frequently returns either too few or too many documents in response to a user query. So, these are the drawbacks, and we would like to mention that Boolean IR model is important, but the IR model does not really prove to be an effective model. However, it captures this important notion of keywords being present or absent, and thereby deciding the importance of the document, which is a good idea and is a foundational notion. So, we proceed and go to the vector model, which is the predominant field in IR today, and it is also based on a pretty simple idea. What it says is that the use of binary weights is too limiting. Okay. So, if you just say 1 or 0, then this hardly is a realistic representation for the document. Non-binary weights provide consideration for partial matches. These term weights are used to compute a degree of similarity between a query and each document. So, these term weights are used to compute a degree of similarity between a query and each document, and ranked set of documents provides for better matching. So, there is a notion of ranking when we retrieve documents. Not all documents satisfy the information need of the user equally, okay? And therefore, it is important to know the degree of relevance of the documents. So, we now proceed to define the vector model, and in this we first say that this weight W I j is greater than 0 whenever a key term in the query is present in the document. W I q greater than or equal to 0 is associated with the pair ith keyword and the document q. The vector of d j is formed by the weights, weight values W 1 j, W 2 j up to W t j corresponding to the t keywords W 1, W 2, W t. Okay. And these are weight values of these t keywords with respect to the document d j. They indicate the importance of the first, second, third up to the tth keyword for the document. Similarly, vector q is obtained from the weight values of these t keywords and seeing their weight with respect to the query q. Now, queries are typically very small, documents are larger in length. So, these weight values have to be obtained in a judicious way. Query is small, the document is large. Okay. So, in this space, in the vector model framework, queries and documents are represented as weighted vectors. Now, if we have the vector model and we have got the query vector and the document vector, then the similarity between these two vectors sim q comma d j is obtained by a cosine similarity measure. So, this cosine similarity measure is nothing but the cosine of the angle between these two vectors, which is obtained as the dot product of these two vectors divided by the product of moduli of these two vectors, and this comes out to be equal to the multiplication at the corresponding positions of the weight values of these two vectors and divided by their modulus. Now, cos of any angle is between 0 between -1 and +1, and in this particular case we never get any negative value because the weight values are always greater than 0. So, this similarity value will come out to be between 0 and 1. Weight values are non-negative. A document is retrieved even it matches the query terms only partially. Okay. So, retrieval is done anyway by the search engine, and it is only the rank calculation or the relevance calculation where cosine similarity measure is used. So, proceeding with more details of the vector model, we get similarity of q and d j as the dot product of the two vectors q and d j divided by the
modulus of these two, magnitude of these two vectors and their product. Now, the key question that comes to our mind is how to compute the weights w I j and w I k. How do we do it? A good weight must take into account two effects: quantification of intra-document contents, the similarity, which is also called the TF factor, the term frequency within a document, and quantification of inter-document separation. This is the dissimilarity, and this is captured by what is called the IDF factor, the inverse document frequency. So, a good weight must take into account these two effects: quantification of intra-document contents, quantification of inter-document separation, the TF factor and the IDF factor. The weight w I j of a query term of a keyword I with respect to a document d j is given as TF I j into IDF I. So, inverse document frequency of the ith keyword multiplied by the term frequency of I in the jth document. So, this is a very simple measure, a very fundamental measure in information retrieval, and this is used, or some variation of this idea is used for ranking. So, formulating this further, suppose capital N is the total number of documents in the collection, N I is the number of documents which contain k I, and frequency I j is the raw frequency of k I within d j. So, this is the term frequency of k I in the document d j. A normalized TF factor is given as f I j, which is nothing but frequency of I in j, that is the term frequency of the ith keyword, divided by maximum over all words frequency present in the document. So, that means we take every word from this particular document and measure their frequency, pick up the maximum frequency amongst all these, use these to divide the term frequency of the ith keyword. Okay. So, this maximum is computed over all terms which occur in the document d j. The IDF factor is computed by a little more complicated formula. IDF I is log of n by n I. So, n by n I is a number which is total number of documents in the system divided by the number of documents which contain the keyword k I. So, n by n I is greater than or equal to 1. So, when this value is 1, that means if a keyword is present in all documents, then taking the log of this number log 1 will be equal to 0. So, the IDF of a keyword which is of a word which is present in all documents is 0. That means, this particular word has no distinct characteristics to give weightage to a particular document. So, this log is used to make the values of TF and IF comparable. It can also be interpreted as the amount of information associated with the term k I. So, log n by n I by n is like something like a probability measure for the keyword, for the presence of the keyword, and n by n I is inverse of that probability. So, negative log of the probability will be something like an information content associated with the term k I. The best term weighting schemes use weights which are given by w I j equal to term frequency into inverse document frequency f I j into log n by n I. This strategy is called TF IDF weighting scheme. For the query term weights, a suggestion is that WIQ is computed in this way. So, why the difference here? The difference is because the query typically contains a very small number of terms, and therefore, the weight has to be found out in a more tricky way. So, this formula is used. Log n by n I is nothing but the IDF term. this multiplies a particular term which is 0.5 plus 0.5 into the term frequency, So, 0.5 addition of 0.5, all these are done to compensate for the fact that query is short in size, a document is much longer, and this kind of addition, multiplication, etc., facilitate coming up with good weight values. So, this formula is difficult to explain, it was arrived at by trial and error, which is like an experimental understanding of the information retrieval researchers or engineers. The vector model with TF-IDF weights is a good ranking strategy with general collections. The vector model is usually as good as the known ranking alternatives. It is also simple and fast to compute. The advantages of the vector model are term weighting improves quality of the answer set, partial matching is allowed, and that leads to retrieval of documents that approximate the query conditions. Cosine ranking formula sorts the documents according to the degree of similarity of the query. The disadvantages are that it assumes independence of the index terms. So, this kind of independence, it is not clear that it is bad. The independence is often an effective idea. So, here is an example which is shown in terms of the keywords K1, K2 and K3, and the documents which contain them. For example, this blue circle shows that the term K1 is present in D2, D4, D6, D5 and D1. If I look at the whole situation from the point of view of documents, then we can represent the documents in terms of their keywords. So, D1 has 100, that means D1 contains only 101. So, D1 is in the intersection of K1 and K3. So, it contains K1 1 here, K3 1 here, it does not contain K2, and therefore, K2 position is 0. Similarly, all these documents are represented in terms of their keywords. We will discuss this example in the next lecture and also move on to other ranking models.